Welcome everyone to this edition of our COMSOC video seminar. Our two speakers for today in order are Toby Walsh from University of New South Wales, Sydney and Data 61, and Lihi Dery from Ariel University. Right, so most of you are probably by now familiar with the format. So a talk is 20 minutes followed by 10 minutes question and discussion. Between the talks, we'll have virtual coffee break, which you are free to join. So Dominic will initiate it after the first talk and the discussion is over. So you'll get an invitation inviting you to join a coffee room. So you wouldn't know who is there before you join, right? So we usually aim to have, I don't know, 5, 6 active participants in each room. This is what is typical, right? And kind of feel free to join, but don't feel obliged. It tends to be a nice device for meeting people and interacting a little bit, making it a little bit more like a real conference. But you know, we also appreciate that many of you may have some other obligations or may want to get a real cup of coffee. Or you can go get a cup of coffee and then join the virtual coffee room, right? And after this is over, we'll have our second talk. Okay, so during the talk, so we ask that you don't interrupt the speaker and we'll mute you to ensure that this doesn't happen by accident, right? But you are feel free to ask questions in the chat. So make sure you can all see the chat box, usually at the bottom of your screen, right? So in the chat, you can type in a comment, something social, or a comment on the talk. You can type in a question. If you do that, please start it by typing question in capital letters. Okay. Okay, so there's an example of a perfect question from Dominic in the chat. Make sure you can see it. So you can also ask a question after the talk is over by raising your hand. So I think, again, by now everyone should be familiar with that functionality. And if you find it easy, you can type in your question in the chat, right? And then we may want to ask you kind of by voice or the speaker will read it. Right, okay, anyway, so that's the format. And yeah, so let's start with our first speaker. So Toby, do you mind sharing your screen?
Sure. Okay. Welcome, everyone. Welcome from around the world. It's wonderful to see everyone virtually, and I'm looking forward in the not too distant future, sometime I hope next year, to see many of you in person. In Australia, where I am, in Sydney, we have a fine tradition of acknowledging the traditional owners of the land upon which we are meeting. And in my case, I will acknowledge the Gadigal people of the Eora Nation, who are the owners of the land upon which I meet, and pass those acknowledgements on to any Aboriginal owners of the lands that you may meet on. I want to talk today about a classic problem, social choice, facility location, and looking at strategy-proof mechanisms for that. Some of what I'm talking about is joint work with some colleagues like Harris. It's a classic problem. You have a bunch of facilities, maybe some warehouses, serving some customers, and you want to be able to locate the facilities. So, for example, to minimize the distances that you have to travel to get to all the customers. There's a whole raft of different problems of this form, maybe hospitals that you want to locate. There might be facilities that you need to be far away from as opposed to near, like rubbish dumps. And it's not just geographical problems, there are also problems of other forms. For example, deciding what the temperature is in a school where you might be sharing some rooms with people. You can see that as a facility location problem, picking the ideal temperature. That's in one dimension. Temperature is a one-dimensional scale, but it may extend to other dimensions. So, for example, if you're trying to pick a committee, a number of people to represent a group of people, then you might need the members of the committee or some member of the committee to be near to every member of that group. So there are a number of dimensions to this problem. Is it one-dimensional, two-dimensional? We've already seen that. Is there a tree or graph underlying this? And different types of distances that I will talk about, Euclidean distances, Manhattan distances, travel time distances that you can have. But what's really important, what makes this perhaps an interesting problem above all to study, is that of course we have a restricted preference domain underneath. You saw the single peak preferences that we had for temperature, and typically we're thinking about preferences of that form. And because of that special preference structure, we can escape some of the Arrovian impossibility results that plague other problems in social choice. So here we have an example, simple example, running example. We're thinking about a 1D facility location problem. We've got 4 agents on the line, 2 facilities we want to locate, and we will consider one of 2 possible objectives. A utilitarian objective where we consider the sum of distances the agents have to travel, trying to minimize that, or an egalitarian objective where we want to minimize the maximum distance that that any agent has to travel. Different solutions you see here, having those optimal egalitarian, utilitarian welfares. We'll also consider one other wrinkle at some various points in the talk, which is that sometimes we'll think about the facilities having bounded capacity. Sometimes the facilities will have unbounded capacity. We won't worry about how many agents are being served by any one facility, but often we'll be thinking about the case where facilities have some fixed capacity, and so agents aren't necessarily served by the nearest facility. And in fact, then a solution is both a location for facilities, but also an allocation of agents to facilities, maybe not the nearest facility, that respects those capacity limits. That you will see has some interesting and knock-on effects and changes the space of strategy-proof mechanisms in quite a significant way. Okay, we'll mostly be thinking about the 1D problem. The 1D problem is interesting. What we've seen that there are instances of problems like the temperature setting problem, which are 1D, or putting warehouses along a highway, or wastewater treatment plants down a river. Those are essentially 1D problems. But the 1D problem also helps us understand more complex metrics. For example, the lower bounds that we'll talk about for the 1D problem are inherited by 2D problems. Okay, and the sort of questions we'll be asking are ones in this setting of thinking about approximate mechanism design. Actually designing mechanisms that are strategy proof or compute optimal solutions may not be tractable and may not be possible. So we're going to look at how well we can approximate those 2 metrics, the utilitarian objective or the egalitarian metric, given that the mechanism is strategy proof. That's a fine body of work that was started by Ariel and Moshe back in 2013. Okay, let's start with the simplest case, one that all of you will probably know already. If we've got one facility, well, a natural thing to do is put it at the median agent. That's strategy proof. And it's also optimal. If you want to minimize the total cost, that's optimal. And it's not a too bad approximation for the maximum cost. That's a 2 approximation of the maximum cost. So that sounds quite a reasonable thing to do. If you really are concerned about the maximum cost, well, putting the facility at the midpoint is optimal, but that's not strategy proof. Of course, you can bias where the midpoint is by misreporting your location. And it's not a particularly good approximation of the total cost. It's an N over 2 approximation for the total cost. So that's what you can do with one facility and 2 agents. What about 2 facilities and 2 agents? The next possible most complex one, well, that's of course trivial again. You just put a facility at each agent. That's strategy proof and optimal for whatever objective you've got there. Okay, 2 facilities and 3 agents. The next most complex one you can do. Well, there's a strategy proof mechanism that's optimal for the total cost. So you've got to consider a number of cases. If one of the facilities is of size 2 and one is of size 1, then you put the facilities at the 2 endpoints, and then depending whether the interior agent is, which endpoint is nearer, you put the bigger facility at that endpoint. That's what you do when you have a facility of size 2 and size 1. If you have facilities with spare capacity, both facilities 2 or bigger, then you just put facilities at the endpoints, and that gives you an optimal solution for the total cost and is strategy proof. That's also not a bad solution again for the maximum cost. It's a 2 approximation for the maximum cost, and you can prove that you can't do any better. That any strategy proof deterministic mechanism can at best 2 approximate the maximum cost. That's the price of strategy proofness, is you've got to be a 2 approximation. Okay, we've done the really trivial cases. Let's ramp up the complexity. Let's go to 2 facilities and any number of agents, n agents. What could we do there? Well, a natural thing to do is the endpoint mechanism. We already saw that with 3 agents. let's put the facilities at the two endpoints, put one facility at the leftmost, one facility at the rightmost. That's strategy proof if you have no capacity constraints. And there's a beautiful result. But that is the unique mechanism that's deterministic, anonymous, strategy proof, and has a bounded approximation ratio for either the total or the maximum cost. So it's hard to say that that's probably not the most natural thing to do if you're worried about these objectives and you want to be strategy proof. But unfortunately, when we throw in capacity limits, it's no longer strategy proof. The blue agent here has to travel a very long distance to the left to the yellow agent to be served by the facility of size 2. And if the blue agent misreports their location a bit to the right, then they will be served by the facility on the right. Don't forget, a solution now is not only a location of facilities, but an allocation of agents to facilities. So if the blue agent misreports their location, they can get a better outcome by being served by the facility on the right. So we lose, the endpoint mechanism is no longer strategy proof. So if we're interested in strategy proofness, which we often are, what could we possibly do? Well, let's look at a simple case where the agents are, there's no spare capacity. We'd have two facilities the same size. You can do the analysis for more complex cases where you have facilities of different sizes, and there is spare capacity. But let's just look at the simpler setting where there is no spare capacity and the two facilities are the same size. Well, we can turn the problem inside out. Instead of putting the facilities on the outmost, put them on the inside, put them at the kth agent and the kth plus an agent in the inside of the line. And you can prove that that is strategy proof, even in the presence of capacity constraints. That's because the solution forces the agents to be served by a particular facility. So, and then you can prove it has nice axiomatic normative properties. It's the unique mechanism that's anonymous, Pareto efficient, and strategy proof. And it provides a okay approximation of the total distance as a k-1 approximation of the total distance, and it's again a 2 approximation of the maximum distance. And it's okay in the sense, well, it is okay because you can't actually do better. You can prove that no deterministic and strategy proof mechanism can have a tighter approximation ratio than k-1 and 2. And what's interesting, what's not on the slide, is that is actually twice as good as in the uncapacitated case. The approximation ratio of the total distance is twice as good as what you get in the uncapacitated case. So somehow, by throwing capacity limits into the problem, making it a tougher problem, we actually can somehow secure a tighter approximation guarantee, where you can only guarantee an n-1 approximation guarantee where there are no capacity limits. You can achieve almost half of that when there are capacity limits, k being half of n. Okay, that was 2 facilities. What if we up the ante and move to 3 or more facilities? Again, there's a beautiful result, but now that becomes a very, very challenging problem. In fact, if you have 3 or more uncapacitated facilities, you can prove that there is no deterministic, anonymous, strategy-proof mechanism that has a bounded approximation ratio for either the total or the maximum distance. So if strategy-proofness is what you want, you're going to have to give up a bounded approximation ratio. And in the capacitated case as well, you can prove a similar result, which is that if you have 3 or more capacitated facilities, then there is no mechanism that's anonymous, Pareto efficient, and strategy proof. Okay, so far we've restricted ourselves to the simplest possible setting where we have a one-dimensional problem. Of course, whilst there are some problems like putting facilities, warehouses along a highway, many problems in the real world have 2 or more dimensions or in more complex metric spaces. So what happens in those more complex spaces? We can inherit those lower bounds that we've got from the 1D problem into the 2D problem, because maybe our problem is essentially 1D, even though it's in a 2D space. So all of those bounds that we've already derived map over into the 2D space. But things may be worse. And actually, as we shall see quite shortly, things do get worse when we move to 2D space. So we'll start with the simplest setting, where, or one of the simplest possible settings, Euclidean space. So we're just using Euclidean distances in 2 dimensions. Now, a natural thing to do is to pick 2 orthogonal axes and apply something like the median mechanism that we saw along each of those 2 axes. And that's, if you've got one facility, that actually seems to be a reasonable thing to do. There's a wonderful result, almost 30 years old now, from Peters and others, that says that if there are an odd number of agents, there's a unique mechanism that's anonymous, Pareto efficient, and strategy proof, and that's that mechanism. You pick an orthogonal set of axes and apply the median mechanism to each of those axes. So you pick the median x coordinate and the median y coordinate, and locate the facility at that point. That is the unique Pareto optimal anonymous strategy proof mechanism for 2D Euclidean space. And unfortunately, you can prove that if you have an even number of agents, there's no such mechanism. And if you move to 3 or more dimensions, even an odd number of agents, there is no such mechanism. You can't have anonymity, Pareto efficiency, and strategy proofness. But at least if you've got an odd number of agents, then the natural thing to do is use a median mechanism along each of the axes. And that's not a bad approximation for the maximum distance. You can prove it's a 2 approximation of the maximum distance, and you can prove that that's optimal, that the no deterministic strategy proof mechanism can be better than a 2 approximation. So you couldn't expect to do better than a 2 approximation. In the case of the total distance, if that's your objective, you can prove that the median, the 2D version of the median mechanism, is a square root 2 approximation of the total distance. We don't know what the exact lower bound is here. We do know it's not 1. You can prove that there is a constant strictly bigger than 1 that you can't approximate to. I don't have a very good bound on that. I think the best number I derived was 1.003. You can prove that, so you can't get the exact answer, the exact total distance. That's not strategy proof. And you can prove that you can only approximate it as within some constant factor. But there's still a gap between the lower bound that we have, well, 1.003 and root square root of 2. So interesting open problem if anyone wants to close that gap. Okay, what about, well, that was with 1 facility in 2D space. What about 2 facilities in 2D space? And you can prove a rather negative result here, that if you have 2 or more facilities in 2 or more dimensions of Euclidean space, then no mechanism is anonymous, Pareto optimal, and strategy proof. And that's with or without capacitors. Even if you throw in capacitors, doesn't change the problem. And that's disappointing because if you remember in the 1D case, we got those axiomatic properties. We've got anonymity, Pareto optimality, and strategy proofness simultaneously. In the uncapacited case, that was the endpoint mechanism that put the facilities at the 2 endpoints. In the capacitor cases, that was the inner point mechanism that put the 2 facilities at the inner points. But when we move to 2 dimensions, you can't get those 3 normative properties together. Okay, well, what about Manhattan space? And actually, I was a bit optimistic when I started thinking about Manhattan space, because Manhattan space is more one-dimensional. It's closer, it's like 1.5 dimensions of space, if you like. It's like two one-dimensional problems. But with 1 facility, you can exactly characterize the mechanisms that are anonymous, Pareto optimal, and strategy proof. There are mechanisms for 3 or fewer agents that have those properties, trivial sorts of mechanisms that locate facilities. But you can prove another impossibility result, which is that as soon as you have 4 or more agents, there is no mechanism that's anonymous, Pareto optimal, and strategy proof. And again, that was rather disappointing because in the 1D case, we could get those facilities. The endpoint mechanism, for example, satisfied all 4 of those properties, however many agents we had. But as soon as we have 4 or more agents with 2 or more dimensions of Manhattan space, you cannot get anonymity, Pareto optimality, and strategy proofness. So disappointingly difficult to achieve those fundamental properties that you would love a mechanism to have. Okay, well, what if you give up Pareto optimality? And that's a natural thing to give up. And in particular, the 2-dimensional median mechanism we saw that we were using in Euclidean space just now that minimizes the total Manhattan distance and is a true approximation of the maximum Manhattan distance, and of course is strategy proof again. So if you can sacrifice Pareto optimality, you can still get reasonable approximation guarantees in two-dimensional, or actually high-dimensional Manhattan space, not just restricted to two-dimensional Manhattan space. So if you're interested in building strategy-proof mechanisms for facility location, what are the 3 take-home messages from my brief little talk today? Well, one is capacities make a difference. We went from locating the facilities at the endpoints of the 1D line to being at the inner side, in the inner points of the 1D line to get strategy-proofness. The Euclidean problem and the Manhattan problem were quite different than the 1D problem, and in fact, significantly seem to be significantly more challenging. And equally, as soon as we got to 3 facilities or more in all of those different possible settings, even on the line in Manhattan space and Euclidean space, it became very hard to achieve normative properties like strategy-proofness and anything else like Pareto efficiency at the same time. So, time for some questions. Yeah, I believe I'm supposed to look at the chat. I can't find the chat now.
Let's first unmute ourselves and thank Toby for the great talk.
Very top here. If you look at this rectangle, how do you?
So there's a question from Bill in the chat about considering non-deterministic mechanisms. Yes, that is, I haven't looked at non-deterministic mechanisms, but people like Ariel have. That is, of course, a obvious response to the fact that these deterministic mechanisms that Amy was giving results there for deterministic mechanisms, their poor properties, you can sometimes, you can achieve better combinations of normative properties and better approximation guarantees if you're willing to have randomized mechanisms. Of course, whether that is satisfactory or not, whether people are happy to have mechanisms tossing coins or not is another question. But certainly you can achieve better combinations of normative properties and approximation guarantees if you go to randomized mechanisms. And the next question from Ariel is, if you drop anonymity, can you get possibility results? Yes, all of those impossibility results are I'm trying to remember what the word is now. It's getting a little late than that. They're strict in the sense that if you drop one of, so you're typically assuming 3 normative properties, anonymity, strategy-proofness, and Pareto efficiency, and they're all exact results, which is if you drop any one of those axioms, you can show that there exists mechanisms that satisfy the other 2 axioms. So they're all strict results. So give up any one of them, anonymity, Pareto optimality, or strategy-proofness, then there are immediately mechanisms that satisfy all of those properties. And that's true for the ones in 2D Euclidean space, 2D Manhattan space, and the ones on the line as well. Harris, are there cases where a negative result for approximate social welfare can be changed to a positive result for approximate Pareto optimality? That's a good question. I imagine that probably is the case. I'm not aware of anyone who's actually answered that question yet, but I imagine that is instead of approximating the welfare, approximating Pareto optimality would be another relaxation that would give you possibilities.
Any other questions from anyone in the audience? So whatever format, typing, speaking. Let me ask a question if you don't mind.
No, of course.
Right, so it's a technical one. I'm trying to understand the innermost mechanism. Yes. How does it work when your 2 facilities have different capacities? Right, so
okay, wow, that's
it.
Okay, so you can prove as soon as you have 2 facilities of different capacities that there is no mechanism that's anonymous, Pareto efficient, and strategy proof. You have to give up, for example, Pareto efficiency. So we have, so for example, in our AAAI paper at the beginning of this year, we we gave a mechanism, it's called the extended endpoint mechanism, that was which was strategy proof, had a bounded approximation ratio, and anonymous, but wasn't Pareto optimal. It forced strategy proofness by sometimes forcing the facilities to be outside the endpoints. So therefore it wasn't Pareto efficient, as a way of forcing the agents to be strategy proof by penalizing them if they try to manipulate the result by moving the mechanism further away. And so you can't, and you can prove as soon as you have facilities of different sizes or spare capacity that you have to give up one of anonymity, Pareto efficiency, strategy proofness.
Okay, thanks. And now we have another question in the chat.
Question is from how can giving up anonymity help? Well, then dictatorial-like mechanisms start to have nice axiomatic properties. So serial dictatorships, for example. I don't know if I read the question. How can anonymity give help by using things like the serial dictator-like mechanisms?
Thanks. Any more questions? So what I saw in the chat now is more of an answer to the previous question than a question.
Yes, yes, this answer answered as well. If there are a bounded number of non-truth agents, that's an interesting question. If you have a bounded number of non-truthful agents, are the results of the worst case effects? I'm not aware of anyone who's looked at that, but that I suspect that is again another response to these negative results, is to see if you bound the number of truthful agents. These, although all of these results are for just one agent misreporting. So, but certainly thinking about bounding the agents, bounding the facilities. For example, we've also looked at just the complexity results about just computing optimal solutions, and fixed parameter like analysis is useful in that setting as well. So that's definitely another direction for future work.
Thanks. Further questions? Yes, I think that concludes the first part of the session. So let's maybe thank Toby again for his talk. Okay. Right. Okay, so Dominic, I think now we need your magic to start the virtual coffee break. So the coffee break will be 10 minutes, and then we'll all come back for the next talk by Lihi.
And I should apologize first to any of you who tried to enter the meeting by entering the riddle's answer, Manhattan 5. I had accidentally put the password as Manhattan 9. So if that caused any frustration, I apologize.
Looks like we lost some participants through the coffee break, so maybe they just decided, to make themselves a cup of coffee and then come back. Let's hope for that. So anyway, our second talk will be by Lihi Dery, and she'll be talking about importing voting techniques into a machine learning problem. So the title is Beyond Majority: Label Ranking Ensembles Based on Voting Rules. Welcome, Lihi.
Hi. So I'm in Israel, and this is joint work with Edith from Tel Aviv University, and with our joint graduate student, Avi Belbin. And before I explain what we've done, I'll walk you through some of the phrases in the title of this paper. So I'll start by explaining in 2 minutes what label rankings are, what ensembles are, and don't worry, I won't be explaining voting rules, and then I'll explain what we've done. So label ranking is a supervised machine learning task, which means you get label data of some sort. Here, the example is pictures, but it doesn't have to be pictures. And then you need to predict the label of the data that you don't know what the label is. There's all kinds of tasks of this format. The easiest one to understand is binary classification, where you're asked a binary question, like, is this a dog? And there's two answers, and hopefully you make the right prediction. Multi-class classification is a little bit more complex because you need to choose the right label out of a few labels. Multi-label classification, even more complex because there's a few labels that might meet the requirements, like what are the objects in this picture. And label ranking, the stuff that I'm dealing with, is to rank the labels according to their relevance. So this is an example of a ranking. Now, it doesn't have to be pictures. As another example, say we have some students and we want to learn preferences of students over courses. So we have some student attributes, some stuff we already know about the students. And then we have the labels. The labels in this case are the courses the students take. And we have some label data. So we have some rankings, some preferences of students over courses. And then we have a new student. And what we need to do is to predict the ranking for this student. So I've shown you two examples. There's many, many more. One is this study originated, label ranking originated from a ranking categories for text. And it's today being used a lot in the biomedical community. These guys are publishing their own papers on ranking protein structures. And a few algorithms exist. There's more and more algorithms being published all the time. The first emerged around 2008. And this is not the focus of this talk. We used in our study, we used two algorithms, RPC and LRT. LRT is a decision tree-like, it has a decision tree structure. And we used these for two reasons. They're baseline, they're like, our LRT is a golden standard, and their code was available. So it was easy to use them. Ensembles. Ensembles is an old idea, often used for classification. And the idea is that instead of taking one model and relying on only one model, we can create many models. And then we can have many opinions, and then we can aggregate these opinions. In this case, it's just an aggregation with, say, majority, and in this case, we got the right prediction. Now, the advantages of ensembles are known for a long time. It means that the mistake of one model can be compensated by the other models, and consequently, ensembles generally exhibit better performance than that of a single model. And this has also been found to be true for label ranking ensembles. There are, to this date, except our work, there is 3 studies that use label ranking for ensembles. So this means that they use some kind of model, and the output is a ranking, and then they aggregate these rankings. The 3 previous papers that we found, they differ in 3 things. They differ in the base algorithm, which they use, which again is not our focus. We just use the LRT, LPC, doesn't matter. They differ in the data sampling ways that they do, and this again is not the focus here. And they differ in the aggregation techniques that they use. This is the focus for us. What they stated in their papers, one paper stated they use majority to aggregate the rankings, and the 2 other papers stated they use average. And it took us a while to decipher what they mean, and we had to correspond with some of the authors, but we found that it's a model ranking in the case of one author, and Bourdain in the case of the 2 other authors. Okay, we're not going to talk about voting rules. I know you all know that, and I know that you know that different voting rules can give us different results. Just maybe a word about model ranking, because it's important here. Model ranking just means that you select the most common ranking. Okay, so now what have we done? Our goal was to learn the best voting rule to be used for the aggregation of label ranking models. So this means that if we have a few models and each model outputs a ranking, the question we asked was, what's the best way that to aggregate them? What will give us the most accurate result? So of course, in order to find that most accurate result, we had to define an accuracy measure, which means we have the true ranking. On one side, we have the predicted aggregated ranking that we received using some sort of voting rule. And we decided to use Kendall-Tau beta. What this measure does is it measures the number of concordant pairs, the number of discordant pairs, and it allows for ties, which is really important, especially because in the predicted aggregated ranking, you often receive ties. So just a simple example, if I have a true ranking in the predicted ranking, one of the labels is switched, the accuracy will be 0.83. Now, two things to note here. First of all, there is a true ranking, okay? Which I know that not every research that deals with voting problems assumes that there is a true ranking. In our case, there is. And the metric, Kendall-Tau beta, we used it because it's very common, but any other metric can be used equally. Okay, so our algorithm went like this. We have as an input, we have label ranking models. We have validation instances, that is, we have dataset examples, and we have a set of voting rules. And what we did is we applied the models, the instances on the models, outputted rankings, and aggregated them according to voting rules, and they computed the average performance, and they outputted the best voting rule. We incorporated this in a label ranking ensemble with our algorithms, the voting rule selector, and I'll explain this in a few slides instead of walking you through this pseudocode. So the first thing we wanted to examine, even before we examined the algorithms, the VRS, is we wanted to examine if the aggregating technique actually matters. I was actually sure that it does, but my co-author wasn't so sure. And we wanted to see if we can find a best rule to use for label ranking. I mean, do we actually need to go into all this VRS stuff, or can we just find a rule that works the best? And again, I had my hypothesis here, but we ran the experiments anyway. We ran them on 24 data sets that are the golden standard. They vary in the amount of instances, that is examples, labels, features. We used 16 semi-synthetic data sets, and then we used 5 real-world data sets that deal with expression levels of genes in the yeast genome. We used a data set of sushi preferences, which I'm sure some of you are familiar with, and then 2 data sets of electoral voting results, which again, more common in this community. And our results were that ensemble models methods perform better than a single model. That's not surprising. We found out of the rules that we checked 7 voting rules, and we found that the Copeland performed the best. That's not, for me, that wasn't surprising either, especially given the accuracy metric. But Copeland did not excel in all of the data sets, and we didn't find a single best voting rule that excelled in all of the data set, and we couldn't find the differences, like why a specific rule excelled in a specific data set. And that led us to the second question and the more interesting part of the research, which was, can we use voting rule selector at the data set level and at the instance level? I do see the chat, so I'll just quickly answer Piotr that yes, we didn't try Kemeny just because of complexity. And I mean, we just chose 7 rules, but you can choose any rule you want, so then as you can code it and it works well. And I'm sure that Kemeny, others in the complexity issue would have excelled here. Okay, so how did we, this is a structure of how we incorporated VRS in an ensemble model. We took a data set, one of the 24 I showed you before, and we used what is called a 10-fold cross-validation, which means we split it into 10 folds. We took the first 9 folds and unified them again and split them again into a train set and a validation set. And the last fold is a holdout fold or the test set. The train set, which sampled from the train set with repetitions and created bags, like small mini data sets. We created, in our case, 50 of these. And with these, we trained our models. Now we trained them using a label ranking algorithm. Again, you can choose whatever label ranking algorithm you want to use. And I told you we used the LRT and RPC. And then we created models. The models are different from each other because they trained on different data. And then when you take an example from the validation set and insert it into the model, you will get a different ranking because the models are different. The rankings may be the same, but they also are usually different. And you need to aggregate these models, these rankings, using voting rules. So what we did, we aggregated the ranking and we compared it with a true ranking using the Kendall Tau beta. And we selected the voting rules that is best and inserted it back to the model. So now we have a label ranking ensemble with a voting rule selector. And like I told you, we have the test set. So now we can take an example from the test set and we can see how well our model performs on these examples that it hasn't seen and hasn't trained on. And this is the results I'm going to show you. So first of all, we saw that our model, our algorithm VRS, reached first place in most data sets. We compared to our Oracle, which is it's an upper bound on how well you can do. And Oracle just is something we computed assuming that you always know which is a best data set to use. So we didn't do as well as the Oracle, but it did win. It was better than Copeland and Borda in model ranking and certainly all of the others. And we showed that learning at the dataset level is valuable. The VRS method obtained an improvement of 58.8% relatively to a single model, and it was just slightly better than Copeland. Now that frustrated us for a while, but the thing is we realized that it can do much better because of the upper bound. There is this glass ceiling. The result is statistically significant. So VRS is statistically significant, better than Copeland, but it can't do much, much better. We also checked how many models we should run. And we found that the results stabilize around 50 models. So that is what we ran. We ran 50 models. Can we do better? Yes, we can. We can develop an algorithm at the instance level. We haven't done that yet, but it's possible to do that. And just if we compute an oracle that does know beforehand what aggregation rule to use, you can see that the improvement is 200%. So there is still room for improvement if anyone wants to run this project. Okay, to sum up, although I'm not finished, but just to sum up, what we've studied is the aggregation subtask of label ranking ensembles, and we've shown that Copeland leads to better performance than the two methods used in previous papers, okay? So Copeland is better than Borda model ranking that was used so far, and that there is not one voting rule that is the best. And then we've suggested an algorithm that actually learns the best voting rule to be used in each case. And we published it in a machine learning venue because implications to machine learning are really straightforward. You know, it's a better algorithm, better predictions, better recommendations. Everyone was happy about that, but this is not the reason I asked to present this to you guys, to the COMSOC community. I think in my opinion, that there are implications for COMSOC. So maybe money doesn't grow on trees, but what I think is that data certainly does grow on trees, on decision tree models. And I think that you can look at this work from a COMSOC perspective and see an easy way to generate ranked preferences with a true ranking. Okay, what do I mean? I mean that if I have the true ranking in the data set, so this part is we can take one true ranking and actually let our models create predictions, create ranked preferences. So I can create as many ranked preferences as I wish. And if I want more ranked preferences, all I need to do is train more models. So if I want to study a scenario where I have 10 ranked preferences, I can, and if I want 100 or 1,000 or 10,000, it's really, really easy. I don't need to go and collect this data from users, and I don't need to go to Mechanical Turk. It's really easy to create this data. What about accuracy? If I want the preferences to be closer to the true ranking or farther away from the true ranking, I can tweak that as well, because I just need to look at the label ranking algorithm that I'm using. If I use a very accurate algorithm, I'll get preferences that are closer to the true ranking. And if I use a label ranking algorithm that does just a little better than random, so this is what I'll get. I'll get much more noise in the data. So I have a variety of preferences that I can create for studies. And what I've seen is that this is of interest to the community. This is a non-exhaustive list of papers that deal with this subject in one way or the other. And I know that some of the authors are now in the crowd, now listening. So I think maybe this can be a valuable method for creating preferences. Some of you may ask yourselves, or me, why not use preflib? I really like preflib, and I thank Toby and Nicholas for maintaining it, and I've donated data sets in the past. I think there's two main differences. One is that in my case, I also have user and attribute features. Sometimes it's important to know some stuff about the user, sometimes it's not. If it's important, so the method I'm proposing, we also have data about the users. And maybe more importantly, is a true ranking is available in this method, in our method. As far as I know, in preflib, there are two data sets, the dot guessing game and the puzzle that have a true ranking. Okay, so the takeaway COMSOC message, data does grow on trees, and it's just an easy way to generate rank preferences with a true ranking. That's for COMSOC. That's it.
Thanks, Lihi, for a very engaging talk. I suggest that, as before, we unmute ourselves and give Lihi a round of applause. Okay, so Lihi did a great job answering the one that here in the chat while she was speaking. I don't see any new questions. Okay, so here's one coming from Bill.
Yeah, so Copland is not notably indecisive in ties. Did you find many ties? And if so, how did you treat ties when the true result is one of those tied? Well, the accuracy measure that I showed knows to treat ties. So it wasn't a problem. As to how many ties we found, I can't tell you off the top of my head. We tried many since, so I think Javi tried this kind of stuff. Like we tried identifying where we find more, all kinds of stuff.
What I'm trying to say is
there's a lot of open research here, and if anyone wants to give it a go. I can talk a lot about what I think can be further done here.
What I'm asking is, if your guess as to the true answer is considered correct when you give several answers, one of which is correct, then you're giving some advantage to voting rules that output multiple ties because they're more likely to be correct. Because they're more likely.
Yeah, sorry. Okay, so in that case, we chose if there is a few ties in the first. If we got a few ties in the aggregation, we chose randomly the correct tie. Yeah. So maybe it's not fair enough, or I don't know.
Okay, so there are two more questions in the chat, first from Piotr and then from Ole.
Piotr, do you have any idea how your way of generating preferences were compared to the Mallows model, or maybe Well, if you told me how to compare, I'd compare. I'm not sure. I don't know. This is another thing that can be tried. Because I mean, you can look at the distributions of what we've created, and again, you can fine tune it in different ways. It depends on what algorithm you're using. And even in the same algorithm, LRT, you can make it strong. You can tune it to be strong, or you can tune it to be weak, just, you know, to cut the decision trees early, and then it's just a little bit better than random. So it's another, I think it's another way of looking at how to create a model, like not in terms of Mallows, but in terms of accuracy. Not sure if that makes sense. Yeah. Okay. Ule, would it also make sense to attempt aggregation at the level of models rather than the rankings they produce? You mean creating, like, I'm not sure what you mean, but do you mean like putting a few different models and then aggregating the results of one model versus the results of another model?
No, so I'm asking this question without even understanding exactly what model means here, but somehow your machine learning thing produces this model, which then produces the ranking. That's what I understood from your picture. Yeah. And then you take all the rankings and aggregate them. But I thought if you try to do some, it would not be preference aggregation. I don't know what it would be. Would it be judgment aggregation or something like this to do the aggregation up at the models? I don't know how the information is represented exactly.
The common way that an ensemble works is that the models have to produce something and then you aggregate that. So sometimes the ensembles, like the most known ensembles, they just produce something that is binary, like yes, no, is it a dog? Yes, no. And then the aggregation is really, really simple. And what I found here is that, okay, label ranking has been studied and we're not the first to do label ranking ensembles, but no one, you know, the people that did it before us, they did an excellent job, but they weren't looking specifically at the aggregations. They were just using what they found the most easiest, like model ranking, or they didn't even call it model ranking, but we know it's model ranking, or Bourdon. Again, without, I think one of them did call it Bourdon.
To me, I think that would be a follow-up on some of the previous questions, but I think it's even more basic. Right? So I'm trying to understand a little bit more the structure of this space. Like what number of alternatives, what number of voters are we talking about typically in the data you considered?
So that's the thing, that each voter is a model. A model is a voter. So you can choose. You can create as many models as you want. We saw that our results, that the accuracy isn't getting better after something like 50 voters. So we stopped at 50. But if you, this is for our use, you know, because we were aiming, my co-authors for machine learning, and we were, from the beginning, we were aiming at the machine learning community. So that's fine for them. But if you use this method to study questions that are more COMSOC in nature, you might want to generate more preferences or less preferences. I don't know, but this is something that can easily be tweaked. You just change the number of models you run.
Okay, that the number of voters and the number of alternatives, so that the number of labels, what was typical?
Yeah, the number of labels, you get it from the data set. So you have a data set, and each data set has a predefined number of labels, and we use 24 data sets that each of them had a different number. Just that's the data we had. It depends on if you bring data that has another number of labels. So that's Marcus, your question is really long.
Sorry if I can add about alternatives, but was it more like 10, 100, 1,000, 10,000?
Excuse me, yeah?
Regarding the number of alternatives, could you just an order of magnitude? Was it typically a few hundred, few thousand?
I can show you, just a minute.
Yeah, I might as well repeat that question. Okay, so that's, defining my question. So the number of alternatives, so was it typically like 10 or like 100 or like 1,000, right? So just so that we can...
Let me see. So it was, the most we looked at was 16, and the least was 4. So the number of, you can see the number of alternatives here. It's between 4 and 16. This is another, there is another field that deals with extreme multi-label ranking. These people are interested in stuff like you have a Wikipedia page and you want to find all of the relevant categories out of something like 16,000 categories. So they're not trying to rank the categories, they're just trying to label the data. And then you have the magnitude is different. You have 16,000 categories. So this is another thing I'm thinking that maybe can be done. Like, what if you don't want to label the Wikipedia page, but you want to rank the Wikipedia page? This also goes into the field of recommendation systems. I know people have started looking at problems, at recommendation problems as machine learning problems, like recommending YouTube videos to users, and then you have the magnitude is different. So it's much bigger, and you also need to work with incomplete information and missing labels.
Okay, good, thanks. Okay, so let's go back to the question.
Yeah, I didn't read Marcus' question yet. You use voting rules that aggregate ordinal rankings, but presumably the outcome should be cardinal. It could assign numerical scores. Okay, so I think, Marcus, what you're asking is, have we tried changing this problem into a regression problem? Because that's what regression problems do. In a regression, it's a prediction, you get accuracy next to the prediction. So the question would be, is this a dog? And you'd get like 90% confidence it's a dog, and another percent of confidence, maybe it's not a dog, but 5% confidence it's a cat or something like this. And then you have scores. Yeah, so maybe not necessarily. I haven't tried doing that, but this is actually something I'm interested in trying to do. And I think that if you do that, I don't think that Copeland it wouldn't be my first choice, right? I would change the way I would look at other voting rules. But that's something, I have a new student now and I'm thinking what to give her. So I'm not sure yet what she'll work on. So that's a possibility.
Okay, great, thanks. We have time maybe for another very quick question if you have one.
I want to put my Zoom room in the chat. If anyone wants to talk to me now, I'll be happy. Just, after we finish this talk. So I'm typing it in here and I'll be in Zoom, like we do in a real seminar where people come to you after the talk. So if anyone wants to, I'll be there.
Okay, that's a good approach. Okay, then that I think concludes the formal part of today's seminar, and indeed feel free to approach Lihi after the talk. So let's thank both of our speakers again. Right, and Bill, is it you chairing next week's seminar?
Yeah, yes, it is.
Do you want to say a couple of words?
I didn't prepare, so.
But yeah, we will have next week's seminar and Bill will be chairing it.
Sorry, I should have prepared.
I will be speaking, so you should all come.
Ah.
Also, we have a poll on the website and on the phone, but we can ask as well to people who are actually here about how often we should meet in the future in the seminar, whether we should keep the weekly meeting or now that like semesters have started, we should reduce.
I should mention that the other speaker will be Juan Ternero, along with Dominic.
So you should definitely come.
Okay. Goodbye, people.
All right. Good to see you all. See you next week.
Seminar now. Yeah, thanks everyone for attending.
Bye.
Dominic, you're not telling us the poll results?
Oh, yeah. So it's
transparency, please.
Yeah. So there are 16 people saying every week, 12 people saying every 2 weeks, and 2 people saying every month. So roughly a tie between every week and every 2 weeks.
Well, depending
maybe every 1.5 weeks.
Every month, every 2 weeks, because these are the less the.
But as Marcus points out, these are actually cardinal values, so we can take advantage of that in the aggregation.
Right, at least it's single peaked.
So in the poll on the website, it's a bit different. So there's a much larger group for every other week, which I think because that includes the people who are not here today, they would have come next week.
People who came last
week not count their votes.
Count your factions.
Okay, bye-bye, everyone.
All right, see you.
Bye-bye.
Bye.